is working. I think it is. All right. So 10.3, here we are. We've made it to 10.3. But here's all the stuff that we've learned up to 10.3, because you're going to have to keep track of all these things and more when we get to the end of this unit, 10.8. So all the stuff that you have right now for figuring out if a theory converges or diverges. First, you learn nth term test. Do you guys remember what that is if you were to summarize it in a sentence? Okay, all right. What? Yeah.
Like where the exponent is. This is like my
No, that's the geometric series, which is coming up next. But nth term test is the one where you take the limit and then goes to infinity of the terms themselves. This looks like a negative, but I'm saying nth term test is this. And if it's 0, then you don't know. If it's not 0, then divergence.
Thing after that one.
That's like an a sub n. That. All right. That's the first thing you ever learned, I believe. Then you guys learn this baseline series, the geometric series that we know converges if set it up. Okay, converges if what? What happened? You remember?
But the R is like less than, it's from 0 to 1.
Right. Yeah, this is a small fraction, basically. Converges if R less than 1, well, between 0 and 1. And it diverges if otherwise. Nice. Okay, very cool. Very cool. Then that was 10.1. 10.2 was integral test. Which, remember, that just says if the sum converges, then the integral converges, and vice versa. If the integral converges, the sum converges. Let me say this. Integral converges if and only if, which means it goes in both directions. Like if this converges, then the other one does, and if this one converges, then the original does. If and only if the sum converges. Okay, that was last time. And then we learned one more thing, which was P-series, geometric. P-series look like P-series look like 1 over n. Now that's the n, whereas the geometric series, the exponent is the n, and then this is raised to a power. Or sometimes you'll see it as like 1 over n to the p, or the whole 1 over n to the p. But these converge. Do you remember when? Well, yeah, that's the idea. But in terms of the p, what should the p have?
Bigger than 1?
Yeah, exactly. The bigger it is, then the quicker the shrink, so then more of a chance of converging. So converges if p bigger than 1, diverges otherwise. Okay, there's all the stuff you've learned. I see you guys trying to squeeze it into the margin like me. I should have told you, I mean, it's in your notes already, but there's a quick little summary. And I forgot, but I want to make a little poster so that you guys have access to it as we learn this stuff. So I'll make little post-it these little big pictures of the stuff we've learned as we learn it. But it might take me a while because I gotta grade your tests, I gotta make your quizzes and stuff like that. But I'll get that done at some point. All right, that's all this stuff you've learned. Keep that in your brain and now add another test called the direct comparison test. But this one is pretty intuitive. Like you would have thought of this yourself almost, even if I didn't teach it to you. It basically says if you get a sum like this, a sequence like this, or a series like that, and you're trying to figure out does this converge or diverge, then you can compare it to one that you know converges or diverges and say this is either bigger or smaller than that, so it must do this, like converge or diverge. So more specifically, if you got a series and there's a bigger series that converges, then the original series must also converge. Or if you got a series and it is bigger than a divergent series, then the original also diverges. So what am I talking about? I'm saying, for example, for this first example, 1 over n cubed plus 1. See if you know a series that is smaller than this, that diverges, or a series that is bigger than this, that converges. Because if this is smaller than a convergent series, then for sure it converges. And if this is bigger than a divergent series, then for sure it diverges. You see what I'm getting at? Okay. Okay, so with this one, this is like a classic example. It's very, very clear to see what you should compare it to, or at least for me, I've done this before. You guys have never seen this before. But do you guys have any idea what I'm about to compare this series to? Not 1 over n exactly. Yeah. No. Okay, yeah, all right. I think the easiest thing to compare it to is compare it to exactly that, because this is just that plus 1 on the bottom. And then well, let me say that later. So I'm going to compare it to this. Do you guys remember if this green series converges or diverges? Good job, because why did you say that? No, okay, that's what I'm looking for. Yeah, it's a P series with P bigger than 1. One of these that I'm highlighting in green right now. Converges because P series with P equals 3, which is bigger than 1. Okay, very cool. So this should behave in a very, very similar way. I mean, adding 1 to n cubed is going to make less and less of a difference as n gets cubed. So these should basically be the exact same series. So I should compare those two. We know this one converges. So please agree with me that if the bottom of a fraction is bigger than the bottom of another fraction, then the entire fraction as a whole, this one would be smaller than this one. Like 1/2 is bigger than 1/3, even though 3 is bigger than 2. Yeah, okay, that's what I'm trying to get at. So all these terms are smaller than all these terms. And this one converges, so the smaller one should also converge. That's all I'm about to write. So I'm going to say since, hang on. Okay. Since that green series converges,
What did you call it? You're not saying it's like if mine's not on totally what I
call it the whole thing again.
no, but like oh Like what could you call it? Like just like compare or like compare stuff or like what is that? You know what I'm saying? Yeah, I have to write it out. Like what would you just call that? Or I'll just write it.
I think you got it. Oh, you mean like, can I just call this F or something?
Or like just like the compared sum, or like can you call it that?
Oh, I see. No, I would just write it out. Or, yeah, I would just write it out to be totally clear. But now I see what you're saying. Yeah. I mean, you can see me writing it out. So I said, since this series converges, and all the terms of the original series are smaller than all the terms of the series that I'm comparing it to. So in other words, and 1 over n cubed plus 1 is smaller than 1 over n cubed. No matter what n I plug in there, that's true. So in other words, this is true for all n. Since that converges and that's true for all n, it must be true that this series also converges. Or maybe say, I'm going to say by the comparison test, by the direct comparison test. The series says n goes from 1 to infinity of 1 over n cubed plus 1 must also. Cool. Yes.
Because it's like n equals 1, I mean, we're starting at 1, why? Because otherwise, technically, like, then you want to be.
Good job. Yeah, I thought about saying that. Yeah, Kean's saying if you plug in -1, then this isn't.
No, I feel like it's valid, but still like positive.
Oh, true.
Because,
No, but this would still.
no, because it's plus 1, so. You get like.
This would be a small decimal. This would be 1 point something. Oh, you're right. Yeah. Yeah. Kean's saying I should have been more specific, but I didn't want to overwhelm you with notation. But it says, since this converges, and this is true for every n, but really it's true for every n bigger than 1, which is kind of implied because this original sum was from 1 to infinity. But maybe to be totally clear, I should have said for all n, that's at least 1. True here. But the important part is that you get that I know that this green sum converges. This small has to be smaller because all its terms are smaller. And so if this converges, then there's no way this is infinite. Like, in other words, if this got a finite number, then how could this get an infinite number if all the terms are small? That's all we said here. Just in fancy words, I guess. Cool. All right. 817. All right, we're in good shape. All right, that next one. Now you guys have the intuition. What am I about to compare this one to? Yeah, 1 over 3 to the n is the most natural one. And you could skip this part. You could just start writing proof if you want, but just to be consistent, I'm going to say compare this to n equals 1 to infinity 1 over 3 to the n. And just so we have it, you guys remember if this dude converges or diverges in green? Yeah, that one converges, but it looks weird. Like you see it and you're like, it doesn't match any of the 4 things that I wrote up there. But it does match one of the things that you wrote up there if you write it like that. Oh, this is geometric and this is 1/3. So smaller than 1, so it converges. So sometimes you have to be a little bit creative about how you rewrite this to make it match one of the baseline series that you know. But in this case, you can rewrite it like that. That's a geometric series. Geo with r smaller than 1. That's why it converts. Cool, and then I write this little sentence and I'm done. So here's me doing that. Let me see if it moves that. It does. So I gotta add some space. Okay. I'm gonna write exactly the same thing up here. So let me do it back. And that green series convergent and my sum. It's the same idea. It's like I'm getting a bigger bottom on the original sum than on the when I'm comparing it to. Therefore, the fraction overall is smaller. So therefore, all of these are smaller than all of these that I just wrote for all n bigger than or equal to 1. Since that's true, by the direct comparison that the original that but also ooh. Cool. You guys good with that question? Okay. And then last one on this page. There's that sum. Intuitively, what would you guys compare this one to? Yeah, exactly. Like compare it to if you haven't seen the pattern yet, compare it to like the function of just n and then like no extra constant added. Right. So I'm gonna compare this to this, compare to the sum from n equals 4 because this one starts at 4. 4 to infinity 1 over square root of n. Okay. You remember if this sum converges or diverges? Wow, good job. I was expecting half the people to say converges, half the people to say diverges. But yeah, everybody's saying diverges because you get it because why? What you compare it to or what you see. Good job. Yeah, this is a P series with P being 1/2. P series being these ones up here. This is 1 over n to the 1/2. So it diverges because P is like 1. Okay, cool. Okay. So now look at this one. This one diverges. So if we're going to compare it to this one, then we better hope that this one also diverges. In other words, we have to check that the original series that I'm circling right now is bigger than this divergent series. Because if this one is infinite, then this one better. If this one is infinite and this one is bigger than an infinite one, then this one must also be infinite. Okay. Do you guys see that I'm subtracting 1 from the bottom, making the bottom smaller, making the whole fraction bigger? Okay. So the only thing that's going to change between the two that we've done already and the one that we're about to do is that we're going to say the original is bigger, so therefore it diverges, but the setup and the like template is exactly the same. So let me make some room. Okay, and then I say since I still didn't like that. Thanks. All right, again, since yeah, all right. Since the series then that diverges and our series that we're trying to get 1 over square root of n minus 1. Oh, shoot. And since all these terms are bigger than all the terms from the series I'm comparing it to, so all n bigger than 4. I'll talk about that if you don't see where I got the 4 in a second. Since that's true for all n bigger than 4, it must be, or by the direct comparison test. By the direct comparison test, the sum from n equals 4 to infinity. 1 over square root of n minus 1 must also diverge. All right, questions on this one? Okay, no, everybody's good with this 4. Everybody's good with the fact that I said this diverges, even though it starts at 4 and not 1, like it was in your notes. Okay, if you didn't think about that, then of course this has to diverge. If you take off 3 terms, those 3 terms aren't going to be the difference between an infinite result and a finite result. So if you take off the first 3, 1, 2, and 3, like that's not going to make a difference whether it's divergent or divergent or convergent. Same thing, like had this started at 3 quadrillion, that doesn't matter because that's a finite number that you're thinking about. So this can start wherever. It's just the general form of the sum determines whether it's divergent. Now it's the starting. Cool. Is good with that? Okay. Cool. So like I said, that one's pretty intuitive. Like it makes sense in your brain. If you're comparing it to something bigger or smaller, then it should determine whether it converges or diverges. However, sometimes you can't use that exact the direct comparison test because that's an example. Okay. Let me talk about the second example first, because this is a clear. It's clear why you need this second thing that I'm about to teach you called the limit comparison test. So let me skip the little box and I'll read you what that says in a second. But pretend you're trying to determine if this series that I'm circling right now converges or diverges. If you were to compare that to a series that you know, which one would you compare it to? From 1 to infinity, 1 over n cubed. Except, how come I can't use the direct comparison test, Jeremy? Yeah, this is minus. So this converges, but this one is technically bigger than the one I'm comparing it to. So yes, this converges, but this one's bigger, so I can't say for sure it has to converge too. But in your gut, you should feel like this is 1 over n cubed. This is 1 over n cubed minus 2. Like they are essentially the exact same series. So this one should converge too, but how do I prove that? I can't compare them because this one's technically bigger. That's why you use the second test that I'm about to show you called the limit comparison test. Limit comparison test, when you can't use the direct comparison test, use this limit comparison. What the limit comparison test does is something kind of weird. This one you would not have thought of by yourself. This is one that says, take your series and the series you're comparing it to, divide the 2, and take the limit to infinity. Even that just there is weird, but that's what you do. And then if you get a number out of that, whether it's 47 or it's 0.2 or it's 0, if you get a finite number out of that, well, as long as it's finite or positive, actually, so not 0, I lied. But 0.3. If it's finite or positive, then the two sides either both converge or both sides. Does that help? Yes, big time. Let me do an example and then I'll tell you about the intuition. Yeah, let's make some progress and then I'll tell you why does this even make sense, or what is this even really doing in normal conversational terms. But let's do an example. We already started this bottom one, so let's do that one. I think this is the table again, which doesn't like when I write on it, so give me a second to show all the borders and all that. Boom, all borders. Okay, let me make them room down here. Again, the two things. Original series that I want to figure out is this one. It's still moving in, we said. Okay, let's find that. Okay. 1 over f cubed minus 2. I'm comparing it to this one. There. You guys already know. Just so we have it on the same page. Comparing it to that. Can't use the direct comparison test because we just talked about this is bigger than this, so I can't say for sure this converges. Only if it was smaller. Okay, so can't use the direct comparison test. I use the limit comparison test, which says take the terms of these and divide them in either order. Doesn't matter which one. I guess I'll just do what would be easier. It doesn't matter. I'm going to use the compared one over the original one. So 1 over n cubed divided by 1 over n cubed minus 2. Does not matter if you already wrote it the other way, you get the same result. Okay, and then you take this limit. So take this limit. Well, let me check. Yeah, actually that would work. You could do L'Hopital's rule, but you would have to do it 3 times, and that might be annoying. Or you can do what?
We keep switch flip.
Yeah, exactly. Like I would simplify this, make this one big fraction, things will cancel, and it's easy to take that limit. So this would be limit and goes to infinity. All right, just picture this in your brain. You got 1 over n cubed, and then this flips. So it will become n cubed minus 2 over n cubed. Yeah? Okay. And then this limit, again, you could do L'Hopital's rule 3 times, or you can just see the top degree is 3, the bottom degree is 3, so therefore this limit must be, you guys remember? Nice, good job. It's the ratio of the coefficients, 1 over 1, because it's just 1. Okay, cool. So I know it's a lot of things to keep track of. Sometimes I tell you 1 means diverges, 1 means converges. Sometimes it's bigger than 1 that converges. Sometimes it's smaller than 1 that converges. This time we got exactly equal to 1 and I'm saying it converges. I'll tell you all the reasoning behind this, but by the limit comparison test. Okay, so by the limit comparison test. That the series that I'm interested in, sum from 1 to infinity, 1 over m cubed minus 2, converge. Okay. Why is it K? Oh yeah, why is it K? That's a mistake. Like Jeremy's saying in the original problem, it says from K equals 1 to infinity, and there's no K's in here. That doesn't make sense. So this should be an N. Or the series should have a K. Okay, so that's the math behind it, but you're not going to remember that in a month when you take the AP test if you don't understand what it's doing. So I'll talk to you about what it's doing after this question. Yes. Correct. Yes, exactly that. Actually, yes, I should have said something about that. Yeah, maybe add on to this. Since this one originally converted. For the geometry, we talked about why, but yeah, you could mention that in your proof, I guess. Okay, but what is this doing? This makes no sense. This is weird. You take 2 series, you divide them, you take the limit, you get a number out of that, so therefore it converges. What the heck? Well, what's going on is that you're taking the limit of a ratio. Like anytime you take a limit as n goes to infinity of a fraction, you're basically, what you're doing is it's a race to see which one grows faster. You know what I'm saying? So you're checking here, does the top grow faster, in which case I get infinity? Or does the bottom grow faster, in which case I get 0? Or are they growing at a similar rate, at the same rate, in which case I get some sort of number out of this, some sort of ratio of coefficient. See what I'm saying? And so therefore, since I got a number out of this, whether it was 1 or 16 or whatever, I got a number out of this telling me these are growing at basically the same rate. So if you know that this highlighted one converges, this one is growing at this blue one that I'm highlighting now is growing at a similar rate, because when I divided them, I got a number out of that. And so therefore, they must act the same way. The top one converged, the blue one must also converge. Had this yellow one diverged, then I would have said this blue one also diverges, but they're growing at a similar rate. Yes?
So then if you plug in a number that doesn't, like that diverges, and then you don't get a real number afterwards, can you say the other one converges, or do you not necessarily?
No, you don't necessarily. It's only conclusive if you get a number out. Which is why up here it was saying the limit has to be finite and positive, as in not negative. Or sorry, as in not 0. It has to be like an actual number. Because if you got 0, then that tells you that the bottom is growing faster. Okay, shoot, but then how much faster? Does that mean for sure it converges? Does that mean for sure it diverges? You don't. Yeah, I mean, I can talk a little bit more about that, but not right now. But no, I'll say that later.
Is this other one a diverging one?
I believe so. Okay, but this one is less obvious. Well, let me check. But I think it's less obvious what you should compare this one to. But let me check what your heart tells you. What does your heart tell you to compare this top series to? I just heard so many. All I heard was a bunch of ends. I didn't hear any specific. Okay. Okay, yeah, you're right. Why 1 over n? What the heck? Where did that come from? I see no 1 over n anywhere on here. Exactly. If you just look at the important parts, as in the biggest part on the bottom and the biggest part on the top, this series is essentially n to the 4th over n to the 5. In other words, 1 over n. So that's what I'm going to compare it to. Series from n equals 1 to infinity, 1 over n. Or if you really wanted to, you could do 1 over 4n if you wanted to. But that shouldn't change it. Okay, so I'm going to compare it to that. You guys remember if this one converges or diverges? Wow, good job. I'm sure for sure everybody would say converges. Feels like it should converge, but it's what's called the harmonic series. It's a p series with p equal to 1, so therefore it diverges. Cool. Okay, and so I'm about to do the limit comparison test, and we'll see what happens. You can probably guess. Okay, so limit comparison test looks like this. Okay, it looks like this. Limit and goes divide one by the other. It doesn't matter which one you do top first. I guess I'll do. Well, let's just be consistent. I'll do the compared one on top versus the one I'm interested in on the bottom. Okay, and then same thing. Last time, keep, change, flip, and simplify. Here's me going fast through that. That would be 4n to the 5th minus n cubed plus 7 on top over n times the top of this one. N times 10 to the 4th plus 10. Am I wrong? Okay. All right. And then if I distribute this n to make my life easier, like to make it easier to compare top to bottom. I get this. And therefore, okay, now well, you tell me without me saying anything, what's the limit of that? Okay, good job. Yep, same idea. You got n to the fifth on top, n to the fifth on the bottom. That's the same the same degree on top and bottom. So therefore, you compare the ratios of the coefficients, and you get 4 over 1.
They don't care.
Okay, so let me finish this, and then I'll answer a question. Since the paired one, this 1 over n diverges, and I got a finite number out of the limit comparison test, that tells me that the original also diverges, which is what I'm about to write after these questions. Kia.
Is it, I mean, you talked about how the AP graders are like trickle these equal signs correctly. Is that a, like, because it technically doesn't equal exactly 4, or does?
But the limit does.
The limit does equal.
Yeah, so this equals it totally fine.
Okay.
Nice. Yeah, good question. What did you have?
I feel really good with the other fraction on top, so I don't know.
Nice.
No, but that's still the same thing, like it.
That's actually, oh, that's a good point. Had I done it the other way, that's a good thing to talk about. Had I done it the other way where I put the original fraction on top, then you get a limit of 1/4, which in your brain you feel like, oh, 1/4, that's smaller than 1, so it must converge if you mix up all your tests. But remember, this doesn't say that. This says if you get a number out of that, then they both act the same. So if the compared one diverges, then this one diverges. Yeah, good job. And then there was another hand. Oh yeah, what's up, Blue?
When you're writing the answer, do you have to say anything about like the other film you used matching the requirements for the test or anything? Like, do you
Oh, like being positive.
or like do you have to talk about the limit being a whole not a finite positive number? Or, like,
No,
it just-
I mean they can figure out that 4 is a finite positive number. Yeah, I see what
It's
you're
like
saying.
the other ones we've had to like.
They explicitly say, yeah, I know what you mean. Yeah, that's true. That's true. Sometimes I tell you they can figure that out themselves. Sometimes I say don't let them figure out anything. You're right. But no, I think in this case, it's obvious enough that 4 is a finite positive number that everybody knows that, like your second grade brother knows that. So it's safe to just say since this is 4 by the limit compared to that. Just perfect. All right, let me write that down and then we'll be done. Since this diverges the limit comparison test. It's also divergent. And here's my work. And I think that's safe to do on the AP test too. Do all your work separately and then write a sentence. Like you don't have to include this again, like the work again in your proof. All right, cool. I was gonna say something. Oh, I was gonna say that if you've been doing your unit 10 homework, I forgot to put that answer key up, but I'll do it. I'm just gonna put up last year's, otherwise it's gonna take me forever to do the homework. So I'll put up last year's, which has me, I think I skipped every other problem or whatever. So you may have to ask me about the even problems or something, but I'm here for questions. I'll put up that answer key and I'll put up all the notes from last year so you guys have access to that. All right, that's all I've got. What's up? Yeah, nice.